All right, we're looking through the morning quiz review over limits, sections 1.2 to 1.3. So for this first section, we are given a graph, and we're asked to find the value of each given quantity. Either each problem is either asking for ordered pair or asking for the limit. Okay, and just to review a bit, the distinction between order pair and limits. Order pair is just the point, right? It's just looking to see, does the point exist on the graph. But limit is asking, does the graph approach the same y value? Does the path of the graph approach the same y value at a specific x value? So if we look at part A, it says find the value of a given quantity. F of -8 is asking for, does f of -8 exist? So we're looking to see at -8, does the graph exist? So if we count down to -8, 1, 2, 4, 5, 6, 7, 8. At -8, we do have an order pair, and the order pair is at y value of 3. So f of -8 is equal to 3. For part B, does the limit exist? So limit as x approaches -8 means, so here's -8. In order for a limit to exist, the graph has to approach the same y value. So we see that if we follow the branch, the branch on the right towards -8, it's arriving at a y value of 3. However, there's nothing on the left side of that x value. So we say the limit doesn't exist because in order for a limit to exist, the graph has to approach the same y value from both sides of that target x value. So limit doesn't exist since there's nothing on the left side of -8. For part C, the limit as x approaches -4. So as we approach -4, we see that the left branch is going down towards -infinity. The right branch is also going down to -infinity. So the limit doesn't exist, but we can say that it doesn't exist, and the behavior of the graph is that both sides of -4, both branches on either side of -4 is going down to -infinity. So this -infinity is not saying that the limit exists. The -infinity is more telling us the visual characteristic of the graph and giving more specific information as to why the limit doesn't exist, because there's an asymptote there, and the graph is approaching -infinity on either side of -4. For part D, the limit as x approaches -1. So -1, we see there's a break in the graph. If we follow the left branch towards -1, the y value is leading us towards +1. As we approach -1 from the right side, we see the y value is approaching +3. So we see there's a disconnect. If there's a disconnect, the limit doesn't exist since there's no agreement on either side of -1. So as we approach -1, there's no agreement in terms of the one-sided limits. For E, f of 3, so we're looking to see, does the point exist at +3? So 1, 2, 3. At 3, we see there's a hole. At 6, at 7, so there's no ordered pair at this point, so we say the point is undefined or does not exist. Limit as x approaches 3. So as we approach 3, we see that the graph is connecting to the same y value. So even though there's a hole, we see that the left side is going towards 7, and the right side is also approaching the same y value of 7. There's a consistency. They are in agreement. They're approaching the same y value. So even though there's a hole there, even though the point doesn't exist, the limit does exist since the graph agrees in terms of approaching the same y value. Next one, as we approach 6, 2, 3, 4, 5, 6. As we approach 6, we see the left branch is approaching 4, and the right branch is approaching 7. So we again see there's no agreement in terms of the y value. There's a break in the graph. This is a non-removable discontinuity, so the limit doesn't exist. Okay, for h, limit as x approaches 9. As we approach 9, we see that the y value goes right through 3. So the point exists, the graph goes right through it. We see the order pair exists, and the graph is connecting right through that point. So the limit is at 3. So if there was a question that was asking for f of 9, then you would say f of 9 is also equal to 3. So if the graph is continuous with no breaks in the graph, then the order pair and the limit will agree with each other. They will give back the same answer. For number 2, identify values of c where the limit exists. So the limit is going to exist wherever the graph is connected. So we know that from -8 to -4, the limit is going to exist with parentheses around, and then from -4 to -1, there's a break. From -1 to now, there's a hole at 3, but we said that the limit exists if there's just a hole in the graph that's causing discontinuity. So even though there's a hole in the graph is the path of the graph is approaching the same y value, so the limit does exist at that point. So we can ignore that and continue right through it. So the limit is going to exist from -1 all the way to 6, and there's a break from 6 all the way to infinity. For number 3, it says sketch the graph of a function satisfying the given values. So let me work this through with a blank copy here. So if I'm given order pairs and limit information and I'm trying to sketch out this graph, we may have graph that look different depending on how we interpret this, but I'm just going to give one way that we can potentially interpret and sketch a graph that satisfy these characteristics. So I think the easiest thing to do first is just go ahead and plot these points, because we know these points will exist on the graph. So we know f of -3 is equal to 5. So at -3 we can plot order pair at 5. F of 1 is equal to 8, so I'm going to plot that order pair 1, 8. We know that f of 6 is equal to 5, so f of 6 is equal to 5. So we have 3 order pairs, and then the rest we have to provide a graph involving limits. So here it says limit as x approaching -3 is equal to positive infinity. So this indicates that there's a vertical asymptote. So if we're approaching a specific x value, and if both branches are going up to infinity, we know that there's going to be an asymptote there. So at -3, I'm going to put a vertical asymptote. Okay, so we know that on either side of -3, we know the graph is going to go up to positive infinity. Okay, I'll connect the rest of the graph later. Let's see, limit as x approaches 1 is equal to -4. So we know that the graph is going to connect to the same y value at -4. However, if you see that here, f of 1 is equal to 8. So the limit is going to exist in a different location than the ordered pair. So that means there's going to be a hole in the graph. So at f of at 1, we know that the graph will connect to the same y value at -4. Sorry. So it's going to be down here at -4. However, the order pair is going to exist up here at positive 8. So this should not be here. Now we're going to connect the graph down to this point. and we can continue the graph up. So we know the graph is going to connect to that hole, okay? And then we're told that finally the limit doesn't exist as x approaches 6. So a number of ways that we can do this. We can have the graph connecting as an endpoint. So if it's an endpoint, we know the limit doesn't exist. Or we can create a discontinuity, jump discontinuity, with the graph connecting to a different place. So we could simply end the graph there, or we can continue. So there's various ways to represent that the limit doesn't exist at 6. Either we can stop the graph at the endpoint, or we can continue and create a break in the graph. So I just chose an arbitrary point as a location of that break. And then, okay. So let's recap here. F of -3 is equal to 5. We have the ordered pair. And the limit is infinity. So on either side of -3, we see the graph approaching infinity. F of 1 is 8. Limit as x approaches 1 is equal to -4. So even though the ordered pair is at 1, 8, the graph is connecting to -4. But there's a hole, so we need to also ensure that every part of our graph passes the vertical line test. So we should not see any points or any graphs that are overlapping each other. F of 6 equals to 5, that's an ordered pair, and then the limit as x approaches 5 does not exist. Okay, let's continue with the rest of algebraically finding limits. So for number 4, the first thing we should always do if we're trying to evaluate a limit algebraically is plug in and see if we get see if we get a real number. So if we plug in, if we get a real number, then there's nothing more that we need to do. That's going to be our answer. But if we plug in into target x value into our expression, and if we get 0 over 0, then that indicates it's indeterminate form, and that we can do we can work with the problem to simplify, reduce, and reevaluate. So in this case, we have a complex fraction. When we plug in 11 halves, we get 0 over 0, and we know that we have to find a way to determine common factors that we can eliminate so that we can reevaluate the limit. So here we have a complex fraction. I'm going to find a common denominator of 5 and x minus 3. So that means I'm going to balance the numerator. The denominator here I'm going to factor. And once I have the denominator factored, I'm going to try and undo this complex fraction. So one way that we can do this is we can multiply this fraction by so multiplying by the denominator. This is the same thing as multiplying numerator by 1 over this 2x minus 1 x plus 1. So that's what we have here. And then once we move this up, we see that we can continue factoring the 22 minus 4x. We see 2x minus 11 is going to appear, and that will allow us to factor out the 2x minus 11 that's causing the 0 over 0. And then now if we reevaluate by plugging 11 halves, we're going to be able to, we're in for all the x's after we reduce the complex, the common factor, we're able to arrive at a limit of -8 over 325. Okay, for number 5, first thing we do is plug in our target x value. If we plug 0 in for x, we get 0 plus 9 is 9. Square root of 9 is 3. 3 minus 3 is 0. 0 over 0, that indicates indeterminate form. Now this is we can approach this problem by using conjugates. So if we multiply by the conjugate of the numerator, so conjugate just means we take the numerator, we take the term, and we just change the sign. So the conjugate of this numerator expression will be 3 plus root x plus 9. So we multiply numerator and denominator by this conjugate, and then we expand. So if we expand the numerator, we get 9 minus parentheses x plus 9. and that will allow us to simplify all the way down to negative x. X and negative x will cancel out, and then we can reevaluate the limit since x was what's causing this 0 over 0. And if we reevaluate the limit, we have negative 1 that remains up top. Plug 0 in for x, we get 3 plus root 9. 3 plus root 9 becomes 3, so 3 plus 3 is 6, so negative 1 over 6. Okay, for number 6, again, we evaluate the limit first by trying to plug in 4. If we plug in 4, we get 0 over 0. And then now we can look to see if we can factor. So we factor the numerator. We're able to pull out a negative 1 and then factor to get 3x plus 1 and x minus 4. The x minus 4 cancels out. We can reevaluate the limit, and we get negative 13 after we plug in 4 and for the remaining x. All right, number 7, this is Squeeze Theorem. So Squeeze Theorem tells us that if we have 3 functions and we're told that they follow this relationship where we have a function that is always below the middle function, which is always below the upper function. So if this relationship is given to you, then we can continue with Squeeze Theorem. So we have this relationship of this upper, middle, and lower function, and we're told that it's continuous all the way throughout, so there's no breaks in the graph. Squeeze Theorem tells us that if we can show that the lower function and the upper function are arriving at the same y value at a specific point, then the middle function will be squeezed in the sense that it must also agree with the value that we found on the upper and lower. So for instance, here's a visual example. So let's say we have an upper function, a middle function that's represented by the dotted line, and a lower function that's that we see here. So if the upper function is arriving at a y value, a specific y value, and the bottom function is also arriving at the same values, then we know that the middle function must also be that same value, right? Just by virtue of this relationship. So if we can plug 1, okay, if we plug 1 into the lower function, we're going to get 5 minus 1, which is 4. If we plug 1 into the upper function, we get 4 as well. So if the lower function, the upper function is 4, then we know that by the Squeeze Theorem, because the middle function must sit between these 2 points, and they agree, we can conclude that the middle function must also have a y value of 4.